Hello, good day, mabuhay. This is Norberto Trinidad. I am a student of Math 221 Numerical Methods. And for today's video, I'm going to discuss the Gauss Seidel method, a solution to system of linear equations. All right, before we go on discussing the details of the Gauss Seidel method, I just want to show you some of the numerical method being used to solve for systems of linear equations. First on the list is Gauss elimination method. It is using the reduced row echelon form, and we are transforming our system of linear equations into augmented matrix form. As you may recall, our augmented matrix has this coefficient matrix, unknown vector, and constant vectors. Now, depending on how did you do the elimination, you can either use forward and back substitution to get the values of the unknown. So the other method is the LU decomposition method. In the LU decomposition method, we are decomposing our coefficient matrix, right, into the equivalent lower and upper matrix. Now it depends on what methods you are using. Sometimes you can see the diagonal ones on the upper and then the diagonal ones on the lower. Actually, the implementation of this one is the method Crouch and Doolittle. Alright, so it depends on what you are using. You will arrive on either the diagonal ones in the upper or in the lower matrix. Another method that we can use to solve for system of linear equation is the Gauss-Jacobi and Gauss Seidel. So these two are both using iterative process to get the values of unknowns. Now, what is the difference? So for the Gauss-Jacobi method, the iteration, every iteration, is using the same set of data from the previous values of iteration. Now, for the Gauss Seidel method, the iteration use the recent data at the time of its solution. So it is not waiting for all the values to be computed, but it is using whatever is the recent values of the variables that is present during the time of its solution. And actually, using this one, it converges faster than Gauss-Jacobi. So meaning to say, in terms of iterative process, it has a lesser number of iterations before it converges into the values of unknown. So it is faster, right? So now I think we are ready to discuss what is the Gauss Seidel method. All right, Gauss Seidel method. So it is a method of iterative successive displacement used to solve for system of linear equations. And there are 5 steps that we need to follow for us to easily implement the Gauss Seidel method. First is to arrange the given linear equations to have diagonally dominant coefficient matrix. So it is the first thing that we need to do for us to converge faster. And sometimes if we fail to do it, there may be a possibility that we will not converge or there are uncertainties in our result. So it is the first that we need to do in doing Gauss Seidel method. The next one is to isolate one unknown in each of the equations. So if we have 3 equations, 3 unknowns, you need to isolate one unknown for each equation. All right. Number 3 is give an initial guess values for the unknowns. Usually it is zeros. Number 4 is set an allowable error limit for the iterative calculations. So as you can see, there will be comparison between the previous and the present values of our unknowns. And that is the error. If the error is small, meaning to say we have higher accuracy, so we need to set our error limit on the desirable values of convergence for our system. After we are done with steps 1 to 4, we are now ready to perform the iteration until the values of unknowns converge, that is determined by our error limit. I think we are ready for example. Given the linear equations 19x minus 13y plus 4z equals to 111, 8x plus 8y plus 17z equal to 10, and then 4x plus 22y minus 13z equal to 128. We need to do the first step, that is arranging the equations. So we need to inspect the diagonals if it is already in the form of diagonally dominant. If not, we need to perform these equalities for us to determine what equations will be in the first row, and so on and so forth. So after determining the first equation, there will be two equations that will be left on our problem. And we need to determine what will be the equations that will be placed on the second row. That is using these equalities for us to determine. Now, after performing these equalities, we can now have our arranged equation. And actually performing that, we will have our first equation to be 19x minus 13y plus 4z equal to 111. The second equation is 4x plus 22y minus 13z minus 128. And 8x plus 8y plus 17z will be our equation on the bottom. Alright, so now you can observe in here that we have the diagonally dominant numbers on our coefficients. Alright, so let's have step number 2. Okay, the next step is to isolate the unknowns. And for the first equation, 19x minus 13y plus 4z equal to 111, isolating x, we will have 111 plus 13y minus 4z all over 19. Now, second equation, to isolate y, 4x plus 22y minus 13z equal to negative 128. So we will have y equal to negative 128 plus 4x plus 13z over 22. Third equation will be isolating the set. So our set will be equivalent to 10 minus 8x minus 8y over 17. Now, after we isolate the unknowns, let's go to step number 3. And step number 3 is just giving the initial guess for the values of x, y, z. Let's say zeros for all the values. Alright. Step 4 is dependent on the user, set an error limit. So let's say we set the error into 0.0001. And after that, we will have to compare our x new versus the old values that we get or we got from the previous iteration, and comparing the error in each of the iteration. If our error is lesser than the set limit, then our convergence is already derived. Alright? Now that we are done for steps 1 to 4, let's perform the iterations. Let's have the table. And for this table, let's have the column iterations, x, y, and z, and their initial values. And let's obtain x from the equations that we derived. So as for y and for z. Alright, for the first iteration, we will solve for the values of x, and we will use the initial value for y equal to 0 and z equal to 0. That will yield to 5.84211. Actually, that is only because y is 0 and z is 0 in here, so that is 111 over 19. And then now, this 5.84211 recent values of x can now be used in solving the values of y. So whatever is the recent available values of the variables can be used on the succeeding iterations or solving the values of unknowns. So for y, we can use immediately what is the present values of x. Of course, for the set, it is still 0. So that will yield to negative 6.88038. Alright, now these two values, the present values of x and y, can immediately be used in solving at the first iteration for the values of set. So instead of using 0 for x and y, we are now using these present values of x and y given 5.84211 and negative 6.88038. So okay, we will use that one and this one also, and that will yield to the value of set equal to 1.07684. Now let us continue iteration 2. We will now use the present value of y, negative 6.88, and then set 1.07, and so on for computing the values of x. So we will now have 0.97772 for x, and that x again can now be used in computing for the values of y, but still the values of z is 1.076. So having said that and evaluating that, we will have negative 5, 34,691. For the values of z, doing the iteration, we will have 2.67725. Iteration 3, we now have 1.62006. For y, negative 4.53073. For z, we have 1,95796. Iteration 4, we have 2.3329293, negative 50482, 1.88466. And for iteration 5, we will have for x 196624, for y negative 506202, and for z we have 2.04507. So as you can see in here, uh, actually it will converge at around 16 iterations and the values are 2, negative 5, 2. So that that's it for the example problem, and let's go for the explanation of my code that I did using the Visual Basic to implement the Gauss Seidel method. Sharing to you my Visual Basic program to implement the Gauss Seidel method. All right, I'm using the Visual Basic form, and as you can see in here, I have text boxes and labels to facilitate the inputs and output display. I am here having these predefined values of variables commonly used for linear equations that a user can choose. And then underneath the enter the variable coefficients are text boxes that will be the placeholder of the user input for the values of our linear equations, the coefficients of our linear equations. And then the initial guess, as we all know, we need it for the Gauss Seidel to commence. Then the tolerance is the user-defined input that will limit the error or will define the accuracy that a user wants for the values of the uh, variables of the linear equations. Okay, and then the number of iteration. Now in my system, the implementation is even if the number of iteration is not being met, but the tolerance is already met, so the iterations will terminate. The program will display the output. In the other way around, if the number of iteration is already reached, the maximum number of iteration, but the tolerance is not yet being met, the program will also, the iteration will also terminate, and the program output will also be displayed. Okay, so start is just to start the program, clear is just to clear these text boxes. So let us start. In here, this is the display of my program. All right, and you need to choose first for these predefined variables before the program can commence. Otherwise, there will be some pop-up message in here that will say, please select your variables. And as you can see in here, I intentionally input the coefficients in the manner or the pattern that it is not diagonally dominant. So I can show you that my system is also handling that arrangement. And then, so I think that's it. Let's start. So upon clicking the start button, I have here some declaration of the local variables that will copy the values in these text boxes for the coefficient variables and the initial guesses, the tolerance, and the number of iterations. So let us just go back. So we will just step, 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 step. So all of those are copied. And in here, sorry, I already stepped on it, but I made a function dominant x that will facilitate the arrangement of the coefficient to have a diagonally dominant pattern. And I will not dwell so much about this one, or we will not step into it. But what it is doing is that, for example, we have these three rows or three equations, and we want to check whichever on the first element of each row is the dominant and should be placed on the first row instead. In here, as you can see, maybe 19 is the dominant one. We cannot say yet, but let us see if the program will check on that and have this 19 minus 13 for 11 be translated to our first row. So let us continue. So again, this sum, the accumulated sum, is just, saying I will add these two, the absolute value of 13 and 4, and then deduct it to the number 19. If the value is less, meaning to say the number is more dominant, maybe or compared to the other rows with the first element. All right, so that is how it is being interpreted by the program. So we will not step on it because it will be an iterative process and many iterations. So let us just continue. And actually, the result will be thrown to the result array. And as you can see here in the locals, here is our original coefficients, not yet arranged. Here is the result. Okay, as you can see in the result, I have the third row that has the lowest value. What it does mean? It means that I have the dominant uh, element on the first, I have the dominant value on the first element of the third row. So that third row should be translated as my first row on the arranged coefficient. All right. So in the coefficient x, I will pass that value. And then after that, I completed this coefficient x arranged value. I will pass that value to the Gauss Seidel solver. Okay. I cannot commence yet the Gauss Seidel solver that you will see later because the coefficient is not yet arranged into a diagonally dominant pattern. Okay, so let us see. Let's continue. So as you can see in here, with the result array, this one is not met, so it will just pass. Okay, let us check another condition. This one is also not met because result 1 is not less than result 0, and result 1 is definitely not less than result 2. So it will just be uh, passed. And this one is being met because result 2 is less than result uh, on the index 2 array is less than result on the 0 array, and result 2 as well is less than result index 2 array is also less than result 1 index uh, 1 array values. So it is met, therefore we will enter inside this if function. Now, as you can see, these coefficients 2, 0, 2, 1, 2, 2, 2, 3 are originally the coefficients on our third row, right? This one, 19 minus 13, 4, 1, 1, 1. But now I am passing to the coefficient x variable into the first row, 0, 0, 0, 1, 0, 1, 2. So meaning to say, after that, we can see that our coefficient x 0, 0, 0, 1, 0, 2, 0, 3 has now these values. So this will be our first row on the arranged coefficient that will be used by the Gauss Seidel. All right, so we are done with the first row. So we have two remaining rows that we need to decide whichever rows will be placed on the second and on the third. So let us continue. Uh, so again, this is another uh, way to see what is the dominant between the two remaining rows on the second element of each rows. So what is more dominant? So we need to identify that. And again, it will be an iterative process. We don't want to dig in it, so I'll just uh, continue and let us see if the result 0 will meet these equalities that is less than result 1. So let us see the locals. Result 0. So as you can see in here, result 0 is less than the result 1. So it is being met, therefore it will enter this value rearrangement for from the coefficients to coefficient x, right? After that, we will terminate the if function, and then we will return these coefficient x values uh, so that we can use it to the Gauss Seidel uh, implementation or the Gauss Seidel function solver. All right, so now that we have this arranged coefficient, uh, these arranged coefficient values are now the holder or the array that contains the correct arrangement. Let us see. Yeah, arranged coefficient. So as you can see in here, 19 is the A11. That is a dominant for all the rows. For A11 position, for A22 position, we have 22. That is dominant for the uh, second element on each rows, dominant numbers. 17 is the dominant for all the rows on the third element position. So we have now the correct positioning of the elements. This range coefficient will be passed as a new variable to the Gauss Seidel solver. So again, uh, I think we select XYZ as our variable, and this is just some initial display on our output. Now we are entering the Gauss Seidel solver, having these arguments: arrange coefficient values, initial guess, tolerant, maximum iteration. This is where the Gauss Seidel iteration actually is being performed. Okay, let us continue. So Gauss Seidel, some variable, local variable declaration, some display update for initial values, and then we will now enter the iteration. So as you can see in here, uh, we are just applying what is actually a direct uh, formula that we did for the isolation of XYZ. So as you can see in here, for example, I have here 19 minus 13 for 111. This 111 will be the coefficient in minus the sum. The sum is the product of the coefficient times the variables. Uh, that is not uh, our interest. Okay, that is not of our interest. Let's say my interest is uh, x. So this will be the variable yn set. So in here, there will be 111 minus the summation of 4 times set, and then minus 4 times set plus 13 times y over 19. So over 19 is this one, right? As you can see. Now, if you really want to know, you can just uh, check it one by one on the locals, but it will be so long for this presentation. So just trust the system and just trust the program. And I've checked it twice, thrice, and yeah, it runs accordingly to what uh, the Gauss Seidel iteration should be. All right. So let's say let us have a break in here just to continue our program, and let us check what will be the values of our pre-val. So pre-val. So again, as you can see, just like on our first iteration in the lecture, we have the initial values for x on the iteration 1 as 5.84210. And then we will now compute for the values of y and values of z on the first iteration. So let us just continue. So it will be a recurring one. So let us just continue. All right. So again, it is testing the convergence, and that convergence will be tested against the new value minus the previous value of the x, new value of the y minus the previous value of the y, and then new value of the set minus the new value of the set. So it's not only the x values that we are checking the tolerance, but all of these, the combination of the three should meet the tolerance that we place. If the test converge happens to be greater than the tolerance, then converge false. And if not converge true, then we will exit the function. So that is how it is working. So, okay. So it's not yet converging. So the iteration will continue. And as I've said, this will continue in many iterations. So we need to jump. Okay, still. So again, after that iteration, it converges after the 31 iteration. Even if I place 100 in here in the maximum number of iteration, upon reaching the tolerance that we place in here on the 31st iteration, the program terminates. All right. And so as our value is 1.999, negative 5.00, 2.000, and the rounded up values having 3 decimal points is 2 minus 5, 2. Of course, the decimal points is not displayed because it will just be 000. Now, let us see some exercise in here. For example, I will just have a tolerance of 0.1. What will happen? Oh, there are many breakpoints, so we need to delete it. I don't know how to delete it at once. So maybe I just continue deleting it one by one. All right. Sorry for that. But yeah, continue. All right. So after placing the tolerance point one, we converge, and we already met even after just 5 iteration. How about if I add some uh, tolerance, so the iteration will be uh, more because of the higher accuracy that we desire. Okay, let's say after that one. So with this number of zeros as the error tolerance, we are having 31st iteration, and not even 100. We already converge. So that's good. How about if you add zero more zeros? Of course, it will just be around 44, and you can see uh, maybe on the 44th value, it's already 2.0000, 5.000, 2000. That's why this is the result. Okay. Now, to check whether our system will have different values if I swap this input, so 13 uh, or 111. Still, this is not yet on the dominant diagonal. This is 8. But let us check if the system will still be capable to rearrange this one. Now, yeah, of course, I check it many times with other inputs, uh, and it's working. So let us see with the same number of iterations and tolerance. Let's start. So as you can see in here, we yield the same value because the system was able to rearrange the coefficients inside the program to have diagonally dominant. Okay, I think that's all. And as you can see in here, it depends on the variables that you chose or you will choose. The display in here will change again. So x1, x2, x3. Okay, let's say ABC, just for fun. All right. So that is for my Gauss Seidel implementation using the Visual Basic Programming. Thank you.